so that you have that to go through as well. Okay. Keep in mind that Friday we have a drop-in session from 10 a.m. to 1 p.m. It will be the same link that you used to enter today. If you have any questions about any homework or need some further instruction. Okay. So your presenter this afternoon is Anna Perez. She actually works for me at the Mission Del Paso campus, and she is out there and can help you with the drug dosage if you're out in that area. Um, we are in the E building in room 108. And then my lab assistant at the Rio Grande campus, Lizeth, she's unable to join us today, but she is the one that handles all the dosage students at the Rio Grande campus. And at the Rio Grande campus, we are located in the A building. That's the big one that looks like a church that's across the street from the H building. And we're in room 250, which is clear at the other end of the building closest to Oregon. Okay? So if you have any questions or if you need Anna to speak louder or slow down, you can raise your hand or type it in the chat, and then one of us will address you. Okay? Anybody have any questions? Okay, Anna, are you ready?
Yes, ma'am. Let me share
Okay.
the PowerPoint. Okay, so hi everybody. So as Diana said, this is for the third semester nursing math. And we're gonna go through some little things before we begin the problems. So things you need to know. Properties of percent solutions and concentration ratios. You also need to know that microdrip tubing means 60 drops per minute. The calories in dextrose and glucose are going to be 4 calories per gram. Technically, it's 3.4 calories per gram, but if it's not specified, you assume it's 4 calories per gram. Then we also need to know the formulas for MAP, BMI, BSA, IBW, calorie needs, fluid needs, and rehydration needs. Note, IBW, calorie, and fluid needs differ for men, women, pregnant women, and children and infants. So we have to check that we're using the correct formula when we're working on a particular problem. And then also recall that when we're dividing fractions, you can flip the bottom fraction and multiply. So for example, in this case, if we have milligrams over kilograms over day, it's the same as putting milligrams over kilograms, all of that over day, which is the same as, remember that whenever you're having a whole number, it is the same as having a 1 in the bottom. So you can rewrite this day as day over 1. So what you can do is flip this bottom fraction into 1 over day, and then you just multiply across. So milligrams per kilogram per day becomes milligram over kilogram times day. And then just some common equivalences. 1 cc or 1 cubic centimeter is the same as 1 milliliter. 1 ounce is 30 milliliters. 1 teaspoon is 5 milliliters. 1 tablespoon is 15 milliliters. And 2.2 pounds makes a kilogram. Now, properties of percent solution and concentration ratios. So a solution with X% strength is made by X grams in 100 milliliters of sterilized water. For example, when you have D5W, it means 5% dextrose in water, which means there are 5 grams of dextrose in 100 milliliters of water. Likewise, D7.5W means 7.5% dextrose in water, which is 7.5 grams of dextrose in 100 milliliters of water. And 0.9% normal saline is 0.9 grams of salt, NaCl, in 100 milliliters of water. Then for ratios, a X to Y solution is made with X grams in Y milliliters of sterilized water. So for example, if you have a 1 to 2000 epinephrine solution, that means it has 1 gram of epinephrine in 2,000 milliliters of water. And if it's a solution that is 50 to 10,000 saline solution, it means you have 50 grams of NaCl in 10,000 milliliters of water. Units. Sometimes when you're given a problem, the units are not necessarily specified. So for liquid medications, for example, if it is administered in a hospital or given by a nurse, we're going to assume it's in milliliters. And if it's at home, we're going to have to put the units as teaspoons. For an IV infusion, for a pump flow rate, it has to be in milliliters per hour, and the drop rate would be in drops per minute. Just note that drops can be written either as GTT or GTTS. It's the same thing. For rounding, some measurements must be rounded to a whole number. So for example, capsules, vials, drops, and tablets have to be rounded to a whole number. But tablets, if they are scored, they could be rounded to the nearest half or quarter tablet. This is only if the problem specifies that it's scored. If it's not scored, then you round to the nearest whole number. For teaspoons, they must be rounded to the nearest quarter. As well, the nursing handbook has some extra rounding rules, and some instructors may have their own specific rounding rules, so it's just a matter of asking them to make sure you are given the solutions as they want you to write them. Any questions up till now? No? Okay. Then let's go through some walkthrough problems. The doctor ordered 30 grams of magnesium sulfate in 1,000 milliliters of fluid. The loading dose is 5 grams in 30 minutes. How many milliliters per hour will the nurse set the IV rate for? Round to the nearest whole number. So, we have to first look at what we have and look at what we want. So, the order is 30 grams in 1,000 milliliters of fluid. And the loading dose is 5 grams in 30 minutes. And we're being asked to calculate milliliters per hour. So we write milliliters over hour equals to, we want milliliters in the top, so we write 1,000 milliliters over 30 grams. We want to get rid of the grams here on the bottom, so we multiply times 5 over 30 minutes. And we want the final answer in hours, so we add the conversion ratio of 60 minutes is 1 hour. This way, we cancel out the grams, we cancel out the minutes, and we are left with the units we want, which are milliliters per hour. And so we're only left with the numbers. So you multiply all the numbers in the top, multiply all the numbers in the bottom, and then divide by each. So 1,000 times 5 times 60 divided by 30 times 30. And when rounded, we get 333 milliliters per hour. Also, disclaimer, I'm not a nurse, so if and when I butcher the names for the medicines, forgive me. Calculate the total milligrams of gentamicin sulfate received in 48 hours. The order is 2 milligrams per kilogram every 18 hours IV. The infant weighs 3,200 grams. So now, let's look at what the order is. The order is 2 milligrams per kilogram, and that is 1 dose. And there is 1 dose every 18 hours. So we have the weight of the infant in grams, which is 3,200 grams. We are being asked to calculate the total milligrams in 48 hours. So we would write milligrams equals 2. So we put the milligrams on top, 2 milligrams per kilogram per dose. 1 dose is every 18 hours. And now, since the weight of the infant is given in grams and we want kilograms, that means we have to do a conversion. So since the kilograms are here in the bottom, that means we put the kilograms on the top. So 1 kilogram over 1,000 grams. times the weight of the infant, which is 3,200 grams over 1. Remember that when you're working with dimensional analysis, you need to keep everything as a fraction. So we use a 1 as a placeholder. So in this case, we wanted to cancel out the grams on the bottom, so we wrote them on top and put the 1 in the bottom. If for some reason we needed to have the grams in the bottom, then we would have put a 1 on the top over and then the grams. And then we want to know how many milligrams in 48 hours. So we multiply times 48 hours and also divide it by 1 since it's a placeholder. So we check our units, that everything cancels out except for the milligrams because that's what we want. So we do 2 times 3,200 times 48 divided by 18 times 1,000 equals 17 milligrams. So the patient is being given 17 milligrams in 48 hours. Calculate the milligram per dose for an infant who weighs 6 pounds 7 ounces who has an order for ampicillin 125 milligrams per kilogram to be divided into 4 equal doses. So our order is 125 milligrams per kilogram, and that has to be in 4 doses. And the weight of the patient is 6 pounds 7 ounces. Now, we are looking for the milligrams per dose for the infant, but our weight is given to us in 2 different units, in pounds and in ounces. So first we have to convert it all to just one single number. So we convert first the ounces to pounds. So we would write pounds equals 2, and our conversion factor, which is 1 pound over 16 ounces times 7 ounces over 1 equals 2. The ounces cancel out, and we divide 7 over 16, which gives us 0.4375 pounds. Now, to that, we add the other 6 pounds, so the total weight of the patient is 6.4375 pounds. Now we're trying to solve for milligrams per dose, so we put milligrams on top. So 125 milligrams per kilogram. Since we have the weight in pounds, we use a conversion factor. So times 1 kilogram over 2.2 pounds times the weight of the patient, 6.4375 pounds, with a 1 on the bottom as a placeholder. And then we need to find the number of doses. So since we want the number of doses in the bottom, then we put 1 over 4 doses. Your kilograms cancel out, the pounds cancel out, and we're left with only milligrams over doses. So we then work with the numbers. So it would be 125 times 6.4375 divided by 2.2 times 4 gives us 91.4 milligrams per dose. Or if you wanted to work this order as just one single fraction, you could do so. So for example, we're looking for milligrams per dose, and we could write this as 125 milligrams over kilogram over 4 doses. So instead of doing like this fraction and this fraction separately, you could put it all together. And then we would add our conversion ratio of kilograms to pounds and then multiply times the weight. And it would still give us the same thing, 91.4 milligrams per dose. This is up to you if you want to add it as a single unit, as a single fraction, or if you want to separate it into 2. But just know that you have both options and both of them are correct. Now, calculate the patient's BMI, body mass index. The patient's weight is 120 pounds and the height is 5 feet 8 inches. So first, the BMI formula uses the height in terms of inches. So we have to convert the feet into inches. So we put inches equals 2, and then the conversion ratio of 12 inches over 1 foot times the 5 feet with a 1 on the bottom as a placeholder. We cancel out the feet, and we just multiply 12 times 5, which gives us 60 inches. Now, to that, we're adding the other 8 inches, so it would be 60 plus 8 for a total height of 68 inches. Then, since we now have the height in only one unit, we work it into the BMI formula. And the BMI formula is the weight in pounds times 703 divided by the height in inches squared. So we just input the numbers. So the BMI for this patient equals to 120 times 703 divided by 68 squared, which was 18.24. And if we round to only one decimal, we look at the second decimal. 4 is lower than 5, so we round down to 18.2. Questions? Okay. If the adult dose of medication X is 400 milligrams every 6 hours, what is the adult dosage for a child who is 35 inches tall and weighs 28 pounds? So we look at our information. We are being asked for what is the dosage. To find the dosage, we need the BSA of the child. BSA stands for body surface area. And you need inches and pounds. So it's the square root of inches times pounds divided by 3131. So we are already given the height and the weight in the units we want. So we just plug in the numbers. So the BSA equals the square root of 28 times 35 divided by 3131, which gives us 0.56 meters squared. We then go into the formula for finding a child's dose, which is the child's BSA multiplied by the adult dose divided by 1.7 meters squared. So it would be the 0.56 meters squared times 400 milligrams, which is the dose for the adult, divided by 1.7 meters squared. The meters squared cancel out, and we are left with 131 milligrams. And that is the dosage for this child. Calculate the amount of calories a newborn has received per kilogram per day. The newborn is receiving Similac 24 milliliters every 4 hours with a caloric value of 20 calories per ounce. The newborn is also receiving an IV of D5W, which is the dextrose 5%, at 3 milliliters per hour. And the newborn currently weighs 6 pounds, 3 ounces. We look at the information we have. So there are 2 sources of calories for this baby, which is the Similac and the dextrose in IV. So for the Similac, we have 24 milliliters every 4 hours, and the caloric intake is of 20 calories per ounce. And for the IV, you have a rate of 3 milliliters per hour, and since it is 5% dextrose, it means there are 5 grams in 100 milliliters of water. And the weight of the patient is 6 pounds, 3 ounces. We're going to have to calculate the calories separately for each solution because they have different calorie values. So first for the Similac. We are looking for calories per day. So we put calories per day equals calories on top, so 20 calories per ounce. Our rate is in milliliters, so we have to use the conversion factor between ounces and milliliters. So times 1 ounce is 30 milliliters times the 24 milliliters over 4 hours. Since we want our answer in days, then we multiply times 24 hours per day. We check our units. The ounces, the milliliters, and the hours cancel out, and we are left with the calories per day, which we want. So then we multiply the top, divide by the bottom. So 20 times 24 times 24 divided by 30 times 4 gives us 96 calories per day. So this are the calories being received by the first thing for the Similac. Now we have to calculate the ones for dextrose. So we still are looking for calories per day equals to, as we mentioned at the beginning, the dextrose is 4 calories per gram times the 5 grams over 100 milliliters times the rate of the IV, which is 3 milliliters per hour, and we have 24 hours in a day. So our units cancel out, and we multiply the numbers and then divide. So 4 times 5 times 3 times 24 divided by 100 gives us 14.4 calories per day. So our total caloric intake for this baby was in total 110.4 calories per day. Now, we have this value, but we're being asked to calculate the amount of calories per kilogram per day. So, first, as we did before, we have to convert the weight into only a single number. So we convert those 3 ounces into pounds. So we set it up as pounds equals to 1 pound over 16 ounces times 3 ounces with a 1 in the bottom as a placeholder. The ounces cancel out, and we have 0.1875 pounds. To that, we add the 6 pounds. So in total, the weight is 6.1875 pounds. Then, now we have the weight as a single number. We can plug it into the formula. We are looking for calories per kilogram per day, and we already have the calories per day, so we add that, 110.4 calories over day, times, we want kilograms, so we add the conversion factor, times 2.2 pounds over 1 kilogram, times the weight of the patient. Since we want to cancel out the pounds that are up here, then in this case we write our pounds in the bottom, so the placeholder goes in the top. So times 1 over 6.1875 pounds. Our units of pounds cancel out, so we are left with 110.4 times 2.2 divided by 6.1875, which gives us 39.3 calories per kilogram per day. So this would be our final answer. So third semester math is really fun. It is more challenging than the ones you've been working for in the first and second semester. So it will take a little bit more practice. It may look a little bit more intimidating, but it's good that you're here because we get to have a review before you have to take the test. So it's just a matter of practice. So at the end of the presentation, when we send you the homework problems, please go through it so that you get more familiar with it, because it is easy to get confused between steps sometimes. At least it was for me when I was learning it. So please ask any questions and just get familiar with it so that it becomes easier for you. Now we're going to calculate the calories needed per day. The female patient is 5 foot 4 inch and weighs 135 pounds. So we're looking for a caloric need. To calculate the caloric need for an adult, we first have to calculate the IBW, and the IBW formula for a woman is equal to 45.5 kilograms plus 2.3 kilograms times the number of inches over 5 feet. So in this case, the height is already given as 5 feet 4 inches, so that means that we only have 4 inches over 5 feet. So we can write it as the IBW equals to 45.5 plus 2.3 times 4, which is equal to 54.7 kilograms. And with that value, then we put it into the formula for the caloric need. So calorie needs equals to the IBW of 54.7 times 30. Caloric needs are a range. So for example, in this case, it's between 30 to 35. So first we're calculating the one for 30. So we have the 54 times 54.7 times 30, which is equal to 1,641 calories per day. And then we calculate the higher end of the spectrum. So 54.7 times 35, which gives us 1,914.5, which we can just round to 1,915 calories per day. So the range of calories that this person needs per day is between 1,641 and 1,915 calories per day. Now, we have to calculate the mean arterial pressure, or MAP, with the blood pressure being 180 over 110. The formula for MAP is systolic plus 2 times the diastolic over 3. So our systolic is 180 and our diastolic is 110. So 180 plus 2 times 110 divided by 3 gives us a pressure of 133. Calculate the milliliters per hour for a patient experiencing a postpartum hemorrhage. The order is to infuse 150 milliliters per hour with additional fluids based on hourly losses. The urinary output is 100 milliliters. Vaginal bleeding is 110 milliliters during the last hour. What should the IV be set for the next hour? Did someone have a question? No. So we have the order for 150 milliliters per hour, and the IV rate has to depend on the amount of fluids lost. So we have the order, which is 150 milliliters per hour, plus the urinary output, which is 100 milliliters per hour, and the vaginal bleeding, which is 110 milliliters per hour. So when you add all of that, we are left with 360 milliliters per hour. So that is the rate that we have for this patient. Now, calculate the milliliters per day and calories per day for a 4-month-old. Intake is 105 milliliters, 110, 105, 110, 125, 110, 20, and 30 milliliters of a formula that is 20 calories per ounce. So to calculate the milliliters per day, first we have to add all of the intakes. So once you add all of those numbers, we have 715 milliliters per day. So that already is your answer for the first question of how many total milliliters per day. And now we have to figure out the calories per day. So we put calories per day equals to, we put calories on the top, so 20 calories per ounce. We have our intake in milliliters, so we use a conversion, 1 ounce over 30 milliliters times 715 milliliters per day. Our ounces and milliliters cancel out, so we are left with calories per day. And we multiply the top and divide by the bottom, so 20 times 715 divided by 30 gives us 476.67 calories per day.
Marilyn,
Yes.
did you have a question?
Yes, I was gonna ask her if she can go back real quick and explain where does the 1 ounce over 30 ml come from? Like, I'm lost where that came from.
Okay, so that one is just the conversion ratio between ounces and milliliters. So for every ounce, there are 30 milliliters.
Okay, just the conversion right there. And
Yes.
then the 20 cal over 1 ounce is the formula, what you have up there.
Yes.
Okay. Okay, makes sense. Thank you.
No problem. Any other questions?
No.
Okay. Right, then let's keep going. So a neonate who is term 1 day old and weighs 7 pounds and 7.5 ounces requires an intake of how many calories per day? So first, we have to have the weight in only one term. So we convert the ounces to pounds. So pounds equals to the conversion rate of 1 pound over 16 ounces times 7.5 ounces with a 1 as a placeholder in the bottom, which is equal to 7.5 divided by 16, which is 0.46875 pounds. Now we add that to the 7 pounds for a total weight of 7.46875 pounds. Now we want to know how many calories per day the baby requires. So calories per day. The formula is that babies need between 100 and 110 calories per kilogram per day. So we are going to go first on the lower end of the range. So first put 100 calories per kilogram per day times, we want to get rid of the kilograms, but we have our weight in pounds. So we add the conversion rate of 1 kilogram over 2.2 pounds times the weight of the baby, which is 7.46875 pounds. The pounds cancel out, the kilograms cancel out, and so we are left with 100 times 7.46875 divided by 2.2, which gives us 339.5 calories per day. That is the bottom of the range. So now we calculate the higher part. So 110 calories per kilogram per day times our conversion ratio of 1 kilogram over 2.2 pounds times the weight of the baby. The weight cancels out, so we multiply 110 times 7.46875 divided by 2.2, which gives us 373.4 calories per day. So when it asks us how many calories does the baby need per day, it has to be between 339.5 and 373.4 calories per day. How many milliliters of epinephrine would you give to a patient who has an order for 1 milligram every 3 to 5 minutes? The concentration is 1 to 10,000. So our order is 1 milligram per dose, and the available is 1 gram in 10,000 milliliters. Remember, when we have a ratio like this, it means 1 gram in 10,000 milliliters. So we are looking for milliliters. So milliliters per dose equals 2. We put the milliliters on top, so 10,000 milliliters divided by 1 gram times the times the conversion ratio between grams and milligrams, so times 1 gram over 1,000 milligrams, times the dose, which is 1 milligram per dose. The grams and the milligrams cancel out, so we just divide 10,000 divided by 1,000, which gives us 10 milliliters per dose. We have an order for medication X, 20 milligrams IM PRN every 4 to 6 hours as needed for pain. Available is 100 milligram per cubic centimeter in a pre-filled syringe. The child's weight is 35.2 pounds. The recommended dosage is 2 to 4 milligrams per kilogram per dose. What is the recommended dosage range for this patient? So our order is 20 milligrams per dose. There are 4 to 6 doses a day, and the available is 10 milligrams per cubic centimeter. The weight is 35.2 pounds, and the recommended dosage is 2 to 4 milligrams per kilogram per dose. We want to know what the recommended dosage for this particular patient is, so we're looking for milligrams per dose. we set the milligrams on top, so we work with the recommended dosage. First, we have to find the lower range, so 2 milligrams per kilogram per dose. We want to get rid of the kilograms, but we have it in pounds. So we use a conversion ratio of 1 kilogram over 2.2 pounds times the weight, which is 35.2 pounds over 1. The kilograms and the pounds cross out, and so we multiply 2 times 35.2, which gives us 70.4, and divided by 2.2 gives us 32 milligrams per dose. Then we do the same, but for 4 milligrams per kilogram per dose. We add the conversion ratio, 1 kilogram over 2.2 pounds, times the weight, 35.2 pounds over 1. The kilograms and the pounds cancel out, so we multiply 4 times 35.2, gives us 140.8, divided by 2.2, which gives us 64 milligrams per dose. So the recommended dosage range for this patient is 32 to 64 milligrams per dose. Now, if the dose is within the recommended dosage range, how many milliliters should be administered? So we are told in the order that the patient is receiving 20 milligrams per dose. We calculated previously that the recommended dose is between 32 and 64 milligrams per dose. So we are giving less than the recommended dose, which means it's safe, but the dose is not therapeutic. But if we want to find how many milliliters per dose, we would put, so the available, they tell us, is in cubic centimeters, but 1 cubic centimeter is the same as 1 milliliter. So we can just write 1 milliliter over 100 milligrams times the dose, which is 20 milligrams per dose. The milligrams cancel out, so it's just 20 over 100, which gives us 0.2 milliliters per dose. Questions? Okay. Now we have to calculate the daily fluid for a dehydrated child that weighs 162 pounds. The formula for oral rehydration requirements in milliliters is, for the first 10 kilograms, you give 100 milliliters, plus for the second 10 kilograms, you give 50 milliliters, plus whatever the weight of the patient in kilograms is, minus 20 times 20 milliliters. So this all is in terms of kilograms, so we convert the pounds to kilograms. So kg equals 2, then the conversion factor, so 1 kilogram over 2.2 pounds times the weight, 162 pounds over 1. Pounds cancel out, and we have 162 divided by 2.2, which gives us 73.64 kilograms. Note, since it says that the child is dehydrated, we use the formula for oral rehydration and not the standard fluid requirements equation, which is different. So that is why we use this one in particular, since the problem specifies that the child is dehydrated. So then the rehydration needs for this child are 10 times 100 for the first 10 kilos, 10 times 50 for the second set of 10 kilos, and then the weight minus 20, because we already accounted for those 20 here and here, and that times 20, which gives us 2,572.8 milliliters that the child needs. Medication X is available in a powdered form for reconstitution to provide 400 milligrams when 20 cc's of normal saline is added. What percent solution is this? So in this one, we're working a little bit backwards. So generally they give us the percent solution, but now they are giving us the milligrams and cc's, and we have to find the percent solution. So Available is the 400 milligrams in 20 cubic centimeters. Remember that cubic centimeters is the same as milliliters, so we could just rewrite it as 400 milligrams in 20 milliliters. And remember that a 5% solution means 5 grams in 100 milliliters, or a 2% is 2 grams in 100 milliliters. So we are looking for grams over milliliters. Since we have the available medication in terms of milligrams, we use a conversion ratio of 1 gram over 1,000 milligrams times 400 milligrams over 20 milliliters. The milligrams cancel out. So we have 400 divided by 1,000 times 20, which is 20,000. And once we divide, we are left with 0.02 grams per milliliter. Now, we are asked for the percent solution. So we multiply that times 100, and it gives us 2% solution. Okay. Any questions? Okay. Insulin concentration is frequently measured as the number of units of insulin in a set volume of fluid. For example, U100 has 100 units per milliliter, and U40 has 40 units per milliliter. It is possible to use a 1 milliliter, commonly referred as a TB syringe, for insulin. About how much more concentrated is U100 solution than a U40 solution? So we are looking for 100% is what percent of 40? So we're looking for percent. We divide one over the other. So 100 units per milliliter over 40 units per milliliter gives us, times 100%. The units cancel. And our result is 250%. So a U100 is 250%, or 2.5 times more concentrated than a U40 solution. Any questions before we jump into the independent problems? No? Okay. Then pull out a piece of paper, a pencil, and a calculator so that we can start working on some independent problems. We have an order for medication X, 600 milligrams IVPB every 6 hours. Available is 0.5 grams over 5 milliliters. The instructions are: add available medication X to a 50 milliliter bag of normal saline and infuse over 1 hour. First question is, how many milliliters of medication X are added to the bag of normal saline? B, what is the total milliliters in the IV bag after adding medication X? C, what rate of infusion should be set on the IV pump? And D, what is the rate in drops per minute when using a microdrip set? I'm going to give you guys some time to work on these. Please let me know in the chat once you're ready, and we will go over the procedure. How are you guys feeling? Are you ready or do you need a little bit more time? Alrighty, so let's go over these because we have some more, so we can go through these first. So, first part is to find how many milliliters of medication X are added to the bag of normal saline. So, we are looking for milliliter per dose. We put the available, so milliliters go on top, 5 milliliters over 0.5 grams times our conversion, since our order is in milligrams, so times 1 gram over 1,000 milligrams times the 600 milligram per dose. The grams and the milligrams cancel out, so we have 5 times 600, which is 3,000, divided by 0.5 times 1,000, which is 500, which is equal to 6 milliliters per dose. Now, the instructions are to add that medication to the 50 milliliter bag. So 6 milliliters plus 50 milliliters means we have a total of 56 milliliters in the bag. Now, they're asking us to find the milliliters per hour, since it is already said that we have to give the bag divided by 1 hour. That means it's just 56 milliliters divided by 1 hour, which is the rate itself. And now we want to find drops per minute. So we said drops per minute. We put the conversion ratio between, so we are told it's a microdrip, so we know it's got to be 60 drops per milliliter times the 56 milliliters per hour. Our milliliters cancel out. And we want it in terms of minutes, so we add the conversion rate 1 hour over 60 minutes. So if you multiply the top and divide the bottom, we get 56 drops per minute. Another way that you could have done this is, well, at least for me, it is you look at, there's a 60 on the top, there's a 60 on the bottom, so those two can just cancel out. And that is why we're left with only 56, and we are left with 56 as our answer. But if it's easier for you to like just multiply all the numbers and divide by all the numbers, then by all means, it gives you the same result. But just wanted to point that out. Let's go to the next problem. So a 5-month-old infant nipples the following amounts of formula over a 24-hour period: 90 cc, 1.5 ounces, 5 capital T, which is tablespoons, 45 cc's, 30 cc's, 3 teaspoons, 12 milliliters, 28 cc's, 40 milliliters, and 1.5 cc's. The caloric value of the formula is 22 calories per ounce. How many cc's did the child nibble in the 24-hour period? Let me know in the chat when you guys are ready to go over it. Does anybody need a little bit more time? Okay, then let's go over the procedure. So we want to know how many cc's total the baby had. So we have to convert the units that are not cc's into cc's. So for example, we're going to convert the 1.5 ounces into cc's. So we don't have an exact conversion between ounces and cubic centimeters, but since we know that cubic centimeters is the same as a milliliter, then we use the conversion ratio with milliliters. So cc's equals 1 cc over 1 milliliter times the conversion rate between ounces and milliliters, which is 30 milliliters over 1 ounce, times the 1.5 ounces over 1 as a placeholder to keep everything in a fraction form. So milliliters and ounces cancel out. We are left with 45 cc's. Now we convert the 5 tablespoons to cubic centimeters. So cc's equals to, again, we convert from cc's to milliliters first, and then use the conversion ratio of 15 milliliters over 1 tablespoon times 5 tablespoons over 1 milliliters, and tablespoons cancel out. So we have 15 times 5, which is 75 cc's. Then, to convert the milliliters to cc's, it's just a 1-to-1. So we just add all the milliliters, which in this case is 12 milliliters and 40 milliliters, for a total of 52 milliliters, which means it's just 52 cubic centimeters. And lastly, we convert the teaspoons to cubic centimeters. So cc's equals 1 cc over 1 milliliter times 5 milliliters over 1 teaspoon times 3 teaspoons over 1. And so the milliliters and the teaspoons cross out, and we have 5 times 3, which is 15 cc's. Now that we have everything in terms of cubic centimeters, we add all the numbers. So 90 plus 45 plus 30 plus 28 plus 1.5 plus 45 plus 75 plus 15 plus 52 gives us a total of 381.5 cubic centimeters total. Now, we got a second question. How many calories did the infant consume in this 24-hour period? I'm going to give you a couple minutes to work this one.
I'm sorry, could you go back to the previous slide really quick?
Yes, sure. There you go.
Okay, thank you.
No problem. All right, so we want to know how many calories the infant consumed in a 24-hour period. So we know that the infant consumed a total of 381.5 cubic centimeters, which is the same as milliliters. And our caloric value for this formula is 22 calories per ounce. So we are looking for calories per day. So we put calories on top. So 22 calories per ounce. Since we can just assume that this is milliliters, like this is the same as writing it in milliliters, we can just directly use the conversion between ounces and milliliters, which is 1 ounce over 30 milliliters times the amount of milliliters consumed, so 381.5 milliliters per day. The ounces cancel out, the milliliters cancel out, and so we multiply 22 times 381.5 and divided by 30, which gives us 280 calories per day that the infant consumed. Now, if the total cc's consumed in the day was 381.5 and the total calorie intake was 280, if the caloric requirement for a 5-month-old is 105 calories per kilogram per day and the infant weighs 14 pounds, how many calories does this infant require? Let me know when you guys are ready. Okay, so let's see. So the caloric requirement, we are told, is 105 calories per kilogram per day. And we want to know how many calories per day the baby requires. So we put calories on top, 105 calories per kilogram per day, times, we have the weight in pounds, so we put the conversion factor, 1 kilogram over 2.2 pounds, times the weight of the baby, which is 14 pounds over 1. And when we cross out the weight of kilograms and pounds, we are left with only calories per day, which is what we want. So 105 times 14 divided by 2.2 gives us 668 calories per day. Now, the question is, did the infant consume the required calories for the 24-hour period? We see that the infant consumed 280 calories per day, but the required are 668 calories per day. So the infant definitely consumed less than the required calories. Now it is asking us whether the amount was excessive or deficient. Since it's less, then it was deficient. And then by how much? Just a matter of subtracting. So 668 minus 280 gives us a deficit of 388 calories per day. We have an order to infuse dextrose 2.5 IV at a rate of 36 milliliters per hour using a microdrip set. Each gram of dextrose is 3.4 calories. How many calories is the infant receiving from the infusion per day? Alrighty, so for this one, the order is for 36 milliliters per hour. The IV, since it's dextrose 2.5, it means 2.5 grams in 100 milliliters of water. The IV calories are 3.4 calories per gram. And since it's saying that we're using a micro drip, oh my goodness, I'm so sorry. The drop rate, since it's a micro drip, is 60 drops per milliliter, and we're looking for calories per day. So calories per day, we put the calories on top, so 3.4 calories over 1 gram times the 2.5 grams over 100 milliliters. The order is for 36 milliliters per hour, and we want to know for a full day, so times 24 hours per day. Grams, milliliters, and hours cancel out, so we multiply all the numbers on the top and divide by 100, which gives us 73 calories per day. Order: Medication X, 0.60 milligrams stat. The medication label has a concentration of 2 to 1,000. How many milliliters will be administered? And the second question is, insulin concentration is frequently measured as the number of units of insulin in a set volume of liquid. For example, U100 has 100 units per milliliter and U40 has 40 units per milliliter. 1 U of U40 insulin is how many milliliters in a regular syringe? Okay, so for the first one, we have an order for 0.6 milligrams, and the concentration is 2 to 1,000, which means 2 grams to 1,000 milliliters. We're looking for milliliters, so we set it as milliliters equals 2. We put the milliliters on top, so 1,000 milliliters over 2 grams. The order is in terms of milligrams, so we add the conversion ratio of 1 gram over 1,000 milligrams times the order. So 0.6 milligrams over 1, the placeholder. The grams and the milligrams cross out, and we have 0.3 milliliters as the answer. As I had mentioned before, it is, let's say you didn't have a calculator for some reason. You see 1,000 milliliters, and 1,000 here, those cross out. So we just have 0.6 divided by 2, which would be 0.3. And then for the second one, U100 means 100 units per milliliter, and U40 is 40 units per milliliter. So we want to know how many milliliters in a regular syringe if you have 1 U of U40. So is 1 milliliter over 40 units. And I don't know if you remember from a previous slide, it says that 1 U, like a 1 U syringe, means 1 milliliter. So we cross out the units, and we are left with 1 over 40, which is 0.025 milliliters, which we can round to 0.03 milliliters. Order: antibiotic medication X, 250 milligrams every 8 hours. Available is antibiotic medication X, 300 milligrams per 6 milliliters. The recommended dose is 75 milligrams per kilogram per day, divided into doses every 6 hours. And the weight of the patient is 13.2 pounds. So we can rewrite our information. The order, 250 milligrams equals a dose with 3 doses a day, since we have to administer a dose every 8 hours. So 24 hours in a day divided by 8 gives us 3 doses a day. The available is 300 milligrams equals 6 milliliters, and the recommended dose is 75 milligram per kilogram per day. The question is, what is the daily recommended dose for this patient? So let's check this one out. So we know the daily recommended dose in milligrams per kilogram per day is 75 milligrams per kilogram per day, but we are looking for just milligrams per day. So we use the recommended dose, 75 milligrams per kilogram per day. And to get rid of those kilograms, we have to multiply times the weight. But the weight, we have it in terms of pounds. So we just multiply times the conversion ratio, 1 kilogram over 2.2 pounds times 13.2 pounds over 1. We cross out the kilos and the pounds, which equals to 75 times 13.2 divided by 2.2 gives us 450 milligrams per day. Now, second question. How many milligrams is the patient getting for each day? Okay, so for working this problem, we need to see the dose. So we want milligrams per day. So we put the milligrams on top, 250 milligrams per dose, and we have 3 doses per day. The doses cancel out, so it's just multiplying 250 times 3, which gives us 750 milligrams per day. Now, by how many milligrams is a daily dose excessive or deficient? And remember that our previous answer of the recommended dose was 450. So that means we take the dose the patient is receiving, which is 750, minus the recommended dose, which is 450. And when we subtract it, it means that we have 300 milligrams per day excessive, which, not good. Oh, and this is the end of the presentation. Do you have any questions? Yes.
Can I ask you to go back to one slide, the one with the insulin unit?
Yes.
Please. Okay, this right here. Okay, thank you.
No problem. Either way, Diana, at the end of this, is going to send you an email with the PowerPoint presentation as well, so you can go over it if you need.
Thank you.
No problem. And
the recording, right?
Excuse me?
Recording too? I think she mentioned the recording.
Yes, as well.
You'll get the PowerPoint, the recording, and then some homework problems. So guys, thanks for coming. I hope that this was useful to you. Yes, Jesse?
Yes, which email will you be sending it to?
Whatever one I sent you.
Okay, thank you. Sorry about that.
Hold on, let me check. I have your EPCC email. Is that the one you want? If not, email me from the one you want and I'll send it to that, okay?
Okay, sounds good. Thank you.
So as I was saying, I hope you found this helpful. Remember that we do it every semester. You'll get the emails from me this afternoon with the materials we discussed earlier. Does anybody have any comments, questions, suggestions? Okay then.
Also, remember, yes,
Yes,
Jesse?
Jesse.
I'm sorry, I just wanted to say that it was very, very good and informative. So I really thank you all so much for taking the time to give us some of these classes.
Well, thank you for that. That means a lot. We've been doing it now for, I think, 3 years. And so I just saw the students getting really worked up about that math exam the first week of class. And so this was a possible solution to help you guys do better. You know, because it's, and especially going into third semester, this is the one where everybody freaks out. So it seems like you guys are doing really well. So I think you're probably going to be fine. But if you need anything, do not hesitate to reach out, okay? That's what we're here for.
Also,
Thank you so much.
remember, we're going to be having the open session on Friday. So Diana's going to email you as well some homework problems. Please, if you get a chance, work through those. And if you have any questions that may not have come up during the presentation, come in on Friday between 10 and 1, and just let us know.
Have a good afternoon, guys.
Thank you so much.
You're welcome.